Hey friends. Today begins chapter 4 of our AP Calculus journey. Again, talking about various aspects of differentiation. In this first one, we're going to talk about something called the mean value theorem. Now, it's not an angry value, it's an average value. That's what we mean by mean. And like all theorems that you've seen so far in calculus, I'm going to read a bunch of words and you're going to be like, what the heck? And then we're going to unpack it and you're going to be like, oh, that's straightforward and logical. This is not a bad theorem at all, okay? But don't get lost in the words. Okay, so we have lots of theorems in calculus. Let me just hide myself there for that first paragraph. Theorems allow us to prove the existence of something. They guarantee that a value exists within a region, or they guarantee that the function will behave in a certain way. Today, we want to unpack the mean value theorem, lovingly referred to as the MVT. Informally, it would state that a function that is well behaved over an interval has a property that the instantaneous rate of change of the function somewhere in the interval will be equal to the average rate of change over the interval. Okay, and now you're going to say, I have no idea what you just said. I'm going to read it one more time, and then we're going to just unpack it, okay? So informally, it would state a function that is well-behaved. Well, first of all, well-behaved means it does what we think a function would do, okay? There's not anything exceptionally weird going on. So a well-behaved function over an interval, so like from A to B, has a property that the instantaneous rate of change, we've already talked about those finding instantaneous rates of change, right? That's just the slope of the tangent line at a specific point. So did you hear what I just said? The slope of a tangent line at a specific point of the function somewhere in the interval will be equal to the average rate of change over the interval. Well, isn't the average rate of change also a slope? It would be the slope using, I had said originally we were going to go from the interval A to B, right? So I could find the slope from A to B just using the slope formula, and I could get an average rate. What we're saying is at some point on that graph, there exists at least one spot where the instantaneous rate of change will be exactly the same as the average rate of change. Could be more than one spot, but the mean value theorem guarantees there's one spot. Okay, so I'm just going to hide myself one more time for this paragraph. So you figure out the average rate of change, that's just slope, from point A to point B. The MVT guarantees that there will be a point C where the derivative at point C, also known as the instantaneous rate of change, will equal the average rate of change for that interval. Okay. Okay, so formally, here's the formal definition. If a function f is continuous on the closed interval from A to B and differentiable on the open interval from A to B, but not including A and B, then there exists at least one number C in the open interval A to B such that the derivative of f at C equals the average slope, which would be f of b minus f of a over b minus a, right? That's just using the slope formula with x equals a as my start and x equals b as my end, okay? Okay, from a graphical perspective, the MVT proves the existence of a parallel tangent line, essentially. There's at least one point C in which in the open interval A to B, where the tangent line to the graph of f is parallel to the secant line segment with endpoints a, comma f of a, and b, comma f of b. The secant line represents the average rate of change over the interval. So I'm just gonna hide myself for 1 second in case I'm in the way of the top of that. And we're just gonna unpack that together for 1 sec here. So you see on this diagram, let me just change colors. Let's go blue. So I have drawn a secant line from point A to point B. This secant line right here represents the average slope of the function from A to B. Now, we are saying there exists at least one point at C where the tangent line at C, which is the instantaneous rate of change at C, right? The tangent line at C, that slope will be parallel to the average slope. Now, most of you are looking at this diagram, I hope, right now and saying, hey, there's more than one in this picture. Is that what you're saying? That's what you're all saying. Okay, so let me clear my ink and let's talk that through. There is more than one. There's one up at the top as well. Okay, so in the diagram to the right, there are probably two parallel tangent lines, but the MVT will guarantee us one. The other one is right about here, so let me put that in. You can see that that line would also be tangent, okay? Awesome. Okay, now what happens if we relax the hypothesis? Okay, so we're just going to look at some different situations here. So what if we had a function that was continuous on the interval, but not differentiable on the interval? Remember, we said both had to happen. It had to be continuous and differentiable. Anytime you relax a hypothesis, the conclusion could still be true, but it doesn't have to be true anymore. The MVT only guarantees it if it's both continuous and differentiable. This sounds very much like an AP style question to me. Okay, so here's a function that is continuous on the interval a to b. I'm just going to hide myself for 1 sec, but fails to be differentiable at a single point. It's not differentiable right where I'm circling my mouse right there. Okay, specifically at x equals 2. Is there a point C in the interval a to b such that the derivative of f at C equals the slope from a to b? Well, let's unpack that. What would the slope look like? Okay, let me just get my, okay, so from a to b, if this is a and this is b, I'm looking at a slope that looks kind of horizontal. If I look at this whole thing, there is no point where I would get a slope that would be horizontal. Now, some of you are going to say, oh, I could draw it right here. I could, but then I could have drawn that, or I could have drawn that, or I could have drawn that, right? Because that's a kink in the graph, there are multiple different tangent lines that I could draw there, okay? So unfortunately, because of that spot where it's not differentiable, there is no point C in this graph, okay? So I'm calculating the slope from A to B, and I get a slope of 0, and I conclude there is no C in the interval 0 to 4 such that the derivative of C, or the derivative of f at C, sorry, would equal 0. Okay, how about a function that is differentiable on A to B, but fails to be continuous on the interval A to B? Now I'll hide myself for a second just so you see the words. Is that even possible? What would that mean? Well, I've given you an example here. This is differentiable on the open interval of A to B, but it fails to be continuous on the closed interval of A to B, specifically because at A, I've got a jump discontinuity there, okay? All right, so I'm just going to put myself back. Okay, so the function is differentiable on the open interval and continuous at every point along the closed interval except at x equals 0. Is there a point C on the open interval a to b such that the derivative of f at C equals the average slope? So f of b minus f of a over b minus a. Again, just to remember, that's just the slope formula. That's getting the slope from point A to point B, okay? Well, let's take a look. Here is the slope from point A to point B, okay? Do we have any spot where we could have a parallel slope? Yeah, you should be able to say it's probably somewhere around here we could get a parallel slope. So around x equals what? Maybe a little after 2 and 2 1/3 or something. Okay, so absolutely, yes, there is a point. Nobody asked you what the point is. They only asked what, or is there a point, okay? All right, so let me hide myself so you see the words. Abby lives 200 kilometers from the beach. She leaves her home at noon and arrives at the beach at 2:30. What is the average rate of change of her distance traveled in kilometers with respect to time in hours? Well, she lives 200 kilometers away from the beach, and it took her, what, 2.5 hours to get there? So 200 kilometers divided by 2.5 hours, she is going an average rate of 80 kilometers an hour. Okay. Abby's average rate of change was 80 kilometers per hour. What does the mean value theorem tell us about her trip? Well, if her average rate of change was 80 kilometers an hour, at some point on that trip, Abby had to have traveled for some instance 80 kilometers an hour. Okay. So the mean value theorem tells us that there must have been at least one moment in time between noon and 2:30 p.m. that Abby was traveling exactly 80 kilometers an hour. Now, notice my wording here. I've talked about what the interval is in the answer. Okay. My A value is noon. My B value is 2:30. Okay. All right. Graph a function that is continuous on the closed interval a to b, but fails to be differentiable on the open interval a to b. Yet, despite this, there is a point C in the open interval a to b such that the derivative of f at C is the mean or the average slope from a to b, f of b minus f of a over b minus a. Okay, go ahead and try it yourself. You can do this, you're smart kids. Okay, so here's my picture. Okay, and so it had to not be differentiable. So I put a kink in the graph right here. So that means I'm not differentiable from A to B. But if I looked at the average slope from A to B, it would look like that. And I can definitely find another parallel line. I could probably find another one. There'd be another one right around here. Okay, but for sure, I have at least one point on that graph, point C we're calling it, such that the instantaneous rate of change at C is the same as the average rate of change from A to B. Okay. Okay, graph a function that is differentiable on A to B, the open interval, but fails to be continuous on A to B, the closed interval. And then because of this, there is no point C in the open interval A to B such that the derivative of f at C is the average rate from A to B. Okay, so go ahead and try it. So I did something like this, okay? I did this cute little interval here, but I had a point of, or a jump discontinuity on A. Because of that, when I go to take the average from A to B, you see I get that very, very steep line, and there's actually nowhere along this path that I can get a parallel tangent line, okay? Yay, you guys are getting this, don't worry. Okay, so this is me saying, hey, can I put this somewhere? And the answer is no, okay? All right, the continuous function f is defined on the interval -4 to 3. That'd be the closed interval because it equals both -4 and 3. The graph of f consists of 2 quarter circles and 1 line segment, as shown in the figure. Find the average rate of change of f on the interval -4 to 3. There is no point, there is no point C, -4, where C is in between -4 and 3, for which the derivative of f at C is equal to the average rate of change. Explain why this statement does not contradict the mean value theorem. So we're saying there is no point. We're saying it's not gonna work. How come that doesn't contradict the mean value theorem? Okay, so give yourself a chance to think about it while I erase my ink. Okay, and here we go. So first thing I'm going to do is I'm going to actually find the average slope, which ends up being -2 over 7. -2 over 7. Okay. All of these guys are going to have positive slopes. This is going to be the same slope. The problem is it probably would have happened right around this turn, and this part here is not differentiable because it's a kink, right? So there is no parallel tangent line. Because of the behavior of the graph, it would have happened around x equals 0. Given that this is a kind of circular, it would have been kind of just after x equals 0 probably, if we can just imagine that curving over. That's when you'd start to get a negative slope there, right? But the graph is not differentiable at that point, and so it doesn't contradict the MVT because the MVT says you have to be differentiable in order to guarantee that 1 point. Okay, so this is not a contradiction of the MVT because it's not differentiable at x equals 0. Okay. All right. Verify that the MVT holds for f of x equals 2x cubed plus x squared minus x minus 1 on the closed interval 0 to 2. Then find the c value that satisfies the conclusion to the theorem. Okay. All right. So if I want to do this, the first thing I'm going to have to do is find the average slope. Okay. Well, I can find the average slope. I know my endpoints are 0 and 2, so it's just going to be f of 2 minus f of 0 divided by 2 minus 0, right? I'm just using the slope formula. Okay, so I go ahead and do that, and I get 9. Now, I need to find a point such that at that point, the derivative equals 9, right? Because the derivative is going to give me the instantaneous change. The derivative is going to give me the c value that I'm looking for. So essentially, I have to take the derivative, set it equal to 9, and then find the x value that makes that happen. Okay? Hopefully, I made that clear. So this is my average slope. In order to get a parallel tangent line at some point c, the derivative of f of x at some value for x has to equal 9. I think I did a better job of explaining it that time. Okay, so I need to get the derivative of f. Well, that's easy. That's going to be 6x squared plus 2x minus 1. And now I'm just going to set that equal to 9 and figure what x has to be. So I'll bring my 9 over to the other side. Looking for, let's divide everything by 2 first. That'll make my life a little easier. Looking for something that multiplies together to give me negative 15 and adds together to give me 1. Doesn't exist, so I have to head to the good old quadratic formula. I'll give you a sec to catch up to me. Or just shut me up and pause me. That would make most sense. Okay, and so that ends up being negative 1 plus or minus root 61 over 6. Negative 1 plus or minus root 61 over 6. So what are we saying? We are saying at 2 specific points, one at negative 1 plus root 61 all over 6 and one at negative 1 minus root 61 all over 6, at those specific x values, the tangent line at those x values for the original function would be parallel to the average rate of change of the function, so the slope from A to B. Okay? So that's roughly 1.135, and I've given you a little picture just to show you. So I have the point A to B here. Okay, so the green graph grows all around. Okay, this green graph here was my original function. And then I've marked the point A to B, and I've drawn in a secant line from A to B. And then I've just shown you the positive one, 1.135. Why have I just shown you the positive one? You should all figure that out by now. Remember, the interval was only from 0 to 2, so I could just ignore the negative. True? Okay. So I've shown you the positive one, 1.135, and shown that the instantaneous rate of change here, the slope of the tangent line at C is running parallel to the secant line that joins A to B. Okay. Clear as mud, hey? Okay. The function f is continuous for negative 2 to 2, And f of -2 equals f of 2, which equals 0. If there is no c on the open interval from -2 to 2, for which the derivative of f at c equals 0, which of the following statements must be true? So take a second and read through them. I'll read them for you, but just think through which one do you think might be the answer. So for -2 to 2, the derivative would have to be greater than 0. For -2 to 2, the derivative would have to be less than 0. For -2 to 2, the derivative exists. And for -2 to 2, the derivative exists, but f is not continuous. And then for some k, where -2, where k is between -2 and 2, the derivative of f at k does not exist. Okay, so which of the following statements must be true? Again, good old AP style question. The answer is must be true. Be careful if you're saying it could be true. Okay, did you figure it out yet? Okay, if the derivative of f of at c doesn't exist, then I'm not differentiable. And if I'm not differentiable, then the derivative of f at k does not exist either. So the answer is E. Okay. The answer will have to be E. All right. The function f is continuous and differentiable on the closed interval 0 to 4. The graph above, which is actually below, gives selected values of f on this interval. Which of the following statements must be true? Okay, so the minimum value of f on the interval is 2. The maximum value of f on the interval is 4. F has to be positive between 0 and 4. The derivative of f has to be negative between 2 and 4. There exists c, where c is between 0 and 4, for which the derivative of f at c equals 0. Well, probably I want to figure out the slope between 0 and 4 first, right? So I'll go f of 4 minus f of 0 divided by 4 minus 0. So that sounds like 2 minus 2 over 4 minus 0, which would be 0 over 4, which equals 0. So because it's continuous and differentiable, E has to be the true one because E actually is the MVT. Okay, if the slope between 0 and 4 ends up being 0, that means there must be a value in between that interval where the instantaneous rate of change or the derivative of f at c equals 0. Okay. All right. The height of a tree at time t is given by a twice differentiable function h, where h of t is measured in meters and t is measured in years. Selected values of h of t are given in the table below. Explain why there must be at least one time where t is between 2 and 10, such that the derivative of h at t is 2. Okay, well, again, I probably want to figure out the slope first between t equals 2 and t equals 10. So I'm going to go 15 minus 1.5 over 10 minus 2. That's going to give me 1.6875. 1.6875. Okay. So explain why there must be at least one time. Well, here's the problem. If there must be at least one time, I didn't just find it, right? Because I didn't get 2. Huh. That sucks. Well, I have to be somewhere between the interval of 2 to 10. Okay. So 2 to 10 itself doesn't work. Let's see if we can find another interval. Okay. So we're going to try now 5 and 3. I just went from 3 to 5. Okay. Now you may ask yourself, why did you do that? I just picked something. Okay. Now I stared at the numbers for a couple of minutes to see if I could find anything friendly, but it's a matter of just finding an interval that works. Okay. So I'm choosing to now look at the interval from 3 to 5, which before you all start freaking out on me, it's still between the interval of 2 to 10, right? We're just trying to guarantee that somewhere I will hit h of 2. We're going backwards, right? Sorry, somewhere I will hit that the derivative of h at t is 2. So the interval from 2 to 10 wasn't a parallel line to 2. So now I'm just looking for other intervals and seeing if I can get a 2 out of some other interval in this table. Okay, and I can do it with the interval from 3 to 5. So if I go h of 5 minus h of 3 over 5 minus 3, that's going to give me 2. Okay, so because h is differentiable on the interval from 3 to 5, and h is continuous on the interval from 3 to 5, the MVT still guarantees that there's at least one t such that the derivative of h at t is 2. The hypothesis of the mean value theorem has been satisfied. Okay, I have found an interval that matches the derivative that I was looking for, so I know the MVT will guarantee that. Okay. Okay. Let G be a differentiable function. Is there a number C? I'll just hide my big old head here for a sec. Is there a number C in the closed interval between -5 and -3 such that the derivative of G at C is -4? Justify your answer. Okay, very similar sort of question. Again, I'm looking for already the derivative to be -4. So I'm looking for an interval between -5 and 3 that the average will be -4. Okay. So take a look at the ones you have. See if you can try and figure something out. Okay. Pause me and think about it. Okay. So I found G of -5 and G of -3. So on the interval from -5 to -3, when I go to figure out the slope of that secant, I actually do get -4. And so I can justify, because G is differentiable on -5 to -3, the closed interval, and G is continuous on -5 to -3. So the MVT still guarantees that there is at least one C such that the derivative of G at C equals -4. The hypothesis of the mean value theorem has been satisfied. You know what, guys? Like, the worst part of this lesson is just wrapping your head around the wording, okay? It's not mathematically hard. You're just taking a bunch of slopes. But what you need to give yourself time to do is just get comfortable with how we are justifying things, what we have to say. And yes, you have to use the words, because I know that that's what you're asking right now. Do we have to write all those words? Yes. The answer is a resounding yes. You have to write all those words. Okay. All right, my friends. So here is your task that you can get going on. And as always, if you have any questions, make sure you're connecting with me. You guys got this. Take care.